two lessons in one because Monday you're going away. Sorry about that. But I actually stay out here about midnight to finish the second lesson. All right, let's start. So, talking about log scale, you need to understand what a log scale is. So we'll talk a little bit about the advantage and disadvantages of a regular Cartesian plane with linear axis and when graphing logarithmic relationship. And then we need to be able to graph some logarithmic relationship on semi-log and log-log axis. We'll think about what happened when we plot those graphs on semi-log or log axis and solve problems using semi-log and log-log axis. All right? So I'm going to start off, ask you to look at the two things, linear scale and log scale. What is the difference between linear and log? Sorry? It's positive, yes. And what else? Think about when you go from one to the other, it's adding, and this one is
adding a power.
Multiplying, correct? So one is add 10, the other one is multiply by 10. So you can see that the difference is this is linear, this is non-linear. So you're going to keep on multiplying by 10. Now, so let's have a look at the log scale itself. What I have done here, I have just enlarged this bit, 1 to 10. So that is 10 to 100, 100 to 1000. All right? That's 0.1 to 1. So I'm actually going to use this to illustrate what happened to every single bit. All right, from 1 to 10, 10 to 100, 10 to 1000. All right? So here, you can see that this is a log scale. Where do I actually do all this tick mark here? Where is 2? Where is 3? Where is 4? Where is 5? Where is 6? Where is 7? Where is 8? Where is 9? How do I actually get that? You don't know. That's fine. So here, if you think about that, log 1 is 0.
Yeah.
Log 10 is 1. Correct?
Yeah.
Now, so if that is 1 unit, what is the proportion of this in terms of 1 unit?
110.
It's not 110? Sorry? Okay. Let's what about take the log of 2? So, 10 to the power of x is 2. So x is log of 2. So this point here, if it is log of 2, it would be 0.3010. So distance from here, it occupies 0.3010. Got it? Yeah? Happy with that? So now, here, let's think about that point over there. Notice that every power of 2 is equidistant from each other. So if you think about 1 to 2, 2 to 4, 4 to 8, those distances are equidistant. So I'm going to highlight that. Oops. Going to highlight that. This distance is actually equidistant to that, 2 to 4 and 4 to 8. Why? Why is that so?
It's scale of
It's scale of 2, but think about that. That is, all right, let me write it on the screen. Make it a little bit easier.
like
That is log of 2, correct?
That's log of
This
2
is log
squared,
of 2 squared, which is 2 log 2, correct? So, therefore, this distance is the same as this distance. To 8, sorry, I should highlight it to 8. So this is 3 log 2, correct? Yeah? So you should see that that is equidistance. That's that point over there. All right? So with that, can you actually tell me where 5 would be? Where would 5 be? All right, where would 5 be?
log 5.
Place log 5. So if you work out, that will be about 0.69. So it's not right in the middle, it's 0.69. Think about this whole thing as 1, so that's the proportion. All right? So now the distance from 1 to 2 is actually the same as distance from 5 to 10. All right? Let's work out log 3 on the logarithmic scale. Where is it placed? And then let's try to answer that question. Oh, actually, no. Hang on. The reason why I say that is it's the same is because one take away that bit is the same as there, which is where that point is. All right? That point.
0.47.
Okay, so that would be
0.47.
0.47. All right? So if that's 0.47, can you work out 6 and 9?
You can work out 9.
You can work out 9 based on 3, correct?
Yeah.
Yeah? And then you can actually work out, once you work out 9, all right, you can work out 6, which is
9 take 3. Oh my.
6 is distance from 3 to 6 is the distance from 1 to 2. That's all. All right, same as this, the idea here. Distance 3 to 6 is the distance from 1 to 2. Same as the idea of 5 to 10. All right, so finally 7, you've got to calculate and work out where the location is. That's it. All right, now dot 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 just means that it goes on and on and on and on and on.
No clue.
All right,
Wait, so
here.
why is the difference from 3 to 6 instead of 1 to 3?
Sorry?
Why is the difference from 3 distance from 3 to 6 instead of 1 to 3?
Because look at the 3 and 6 based on this thing. How you calculate that? 1 to 2 is 1 over 6. 3 to 6 is, all right. 3 to 6 is that. Take away that. All right. That 1 to 2. That is double that. If you look at the log, this is log 3. All right. This is log 6, which is log 2 times 3. Yeah?
Log 2.
2 times 3. Log 2
Log 2 plus
log
log 3. Right.
plus log 3. Yeah? Yeah.
So how does that explain the first one?
What's log 2? Sorry?
The 1 and 2 and the 5.
1 and 2 is a 5. 5 is 0.69. So 1 take away that. 10 take away that. That's 1 take away that. It's equidistance for that. That's all. 0.31. Okay? I mean, all this, you really don't need to know that. As long as you know the log, you can plot the point. But let's not worry too much about that. So, the most important thing for you to know, this is just trying to show you what log scale is like. Alright? It's not linear. So a log scale is a scale of measurement for which the relatively large or small quantities are represented in using a more manageable numbers. So things like Richter scale, pH scale, and decibel, loudness, all those are logarithmic scale. I will go through that and do some examples a little bit later. Now, why do we need log scale? Log scales are useful when the data you're displaying is much less or much more than the rest of the data when percentage differences between values are important. So if you look at something like this, these are the same graph. Revenue by production line and revenue by production line. This is plot on a linear graph. If you look at the linear graph, that is actually really small. But if you plot on the log graph, you can see that that actually is not that tiny. All right? So sometimes it's useful when you plot graph. Especially for me, when I was an engineer, I would use log or semi-log graph to do a linear regression. It's a lot easier that way. And then I will transform it back. It's just a transformation.
What is log?
All right? So here, if you look at two things. Here, when we plot this graph here, it's an exponential graph. What is this? Y equals to what? Can you work it out? Y equals to?
Log 2.
Log or exponential?
Exponential.
Exponential. So it is exponential, and it will be, look at this point. Yeah, to the 12x. So what I've done is, if I plot it in the normal Cartesian plane, linear and linear, here you can really it's really hard for you to tell the difference between those points, correct? Yeah? But if I take a log here, which means I have actually enlarged this bit. Yeah? Enlarge this bit, 10, and then enlarge to 10 to 100, and enlarge 100 to 1000. So when you plot it in that situation, you actually get a straight line.
So you just plotted log base 10 of that exponential.
Basically, what you would do is you'll be given a graph like this.
Yeah.
It's the same. This will be 8. This will be 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. 11, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 100, 200, and so on and so forth.
So it's not an even spacing.
Yeah, it's not an even spacing. So what happened is you have enlarging the bottom bit, and you can actually see that as a straight line. So for me, like I say, some of the work that I've done as in my engineering work is I need to be able to use the whole range. So I actually can't really fit a line here. I have got to take it to a log.
That's
Semi-log.
log base 10, right?
Yeah, log base 10. Yeah,
So you're
semi-log
taking
logs.
the
Log base 10.
base 10 of that exponential.
Yeah.
essentially.
You do log base 10 is because you do really need to plot 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Yeah.
So you always use log base 10 in this
Yeah.
situation. All right. So now the semi-log graph. There are two types of semi-log graph. You've got a log linear, where the log is on the y-axis, or linear log, where the log is the x-axis. Now, can you notice the difference in the first one? Which one is a straight line?
Red.
The red is exponential. This is just fx equals to x, like y equals to x, which is a straight line in the linear, but in this situation, it's a curve. And when it is a log, it is a curve. So if you do a log linear graph, when you plot an exponential function, it is a straight line.
Yeah.
Whereas a linear log graph, exponential is a curve, fx equals to x, which is a straight line in linear, becomes a curve, and log x becomes a straight line. Yeah? Because you are taking the log of x here, the x will be straight line. Whereas this one, you are taking that to exponent of 10, so therefore, if this is a log scale, this is a straight line. All right? Now, example 1. Can you show algebraically that all exponential relationship of the form of y equals to AR to the bx will appear as linear relationship of log linear scale? The way to do this is actually take log base r of y, the left hand side, the right hand side, log of base r. So if you take log of base r, you know that log r y equals to log r brackets ar to the power of bx. Now, using your log laws, you should be able to split that out, which means log r of y equals log r of a plus log r of r to the power of bx. Now, what would this be? Log r of a. A is a number.
Point as well.
It's just a constant. Yeah, it's constant. Now, what are you going to do in this case? What would that happen? Log r of r to the power of bx.
Pull out the BX.
It will become
BX.
bx. So therefore, in this form, compare that to y equals to mx plus c.
Yeah.
Log y is y, log r of a is c, n is the b, and x.
Wait, sir.
Yep.
But don't you always use base 10 for the log? So,
No, you don't have to.
or you don't have to.
You don't have to. You don't have to. But
For
I
this
want to use this as a generalization to show how you get that.
If you took base 10, would you still get a straight line?
Which base 10, yes, you would definitely get a straight line
Just
as
a
well.
different form.
Yeah, just different form.
Okay, yeah.
All right. So now, can you describe the gradient of the line formed by this? All right. So if I use log of base 10, what would happen here? Log of base 10. Now I'm doing base 10 now. Log of y is variable because y changes based on x, right? So now if y to the equals to 2x, if I plot a log linear graph, I've got log 10 of y equals log 10 of 2x. So therefore log 10 of y equals x times log of 2. And what is log of 2?
Constant.
It's a constant. It's a gradient. Correct? So in this context, what it is saying that for every increase of x, there's an increase of log of 2. That's all. All right?
Yeah.
Pretty. It's just a matter of interpreting it. All in context. So that is the log linear. I generally, in my situation, I've used a lot of log linear. I haven't really used a lot of linear log. Because I do, when I was modeling, I did a fair bit of exponential. So I need to bring it to a straight line, so I use a log linear. I seldom use log to actually model something. All right, now, so can you actually therefore graph this on the log linear scale? First, you need to change it to y equals mx plus c format.
Increase x once.
All right?
2x
So
plus
how do you change that?
7.
So here, I give you the y-axis is a log 3, log of 3.
What's log 3?
All right.
That is...
So log of 3, basically this is 3, this is whatever.
It's 3.
If you work it as a linear.
2x plus
So this is log of 3. So what you could do in this situation is take log of 3 on both sides. Take log of 3 on both sides.
This today.
Why are you doing base 10?
All right. Here, once you have done that, you should be able to work out
Definitely pretty good.
that is actually log of 327 plus log 3 of 2x, correct? 3 to the power of 2x, yeah?
Yeah, which is
Got it?
2x plus 3.
So let's just become log y is 3 plus 2x or 2x plus 3.
Yeah.
And then of course, here you can start off with the y-intercept is 3.
Yep.
And keep going to x to x to x until you get all the point. All right? Oops. Until you get the points and you can draw a straight line. So remember, this is no longer linear.
No, that's
This is just a log. The scale here is a log scale.
2x.
And that is a linear scale.
3.
Log linear.
Here we go.
Can you hold it down? Actually, doesn't go the other
All
way.
right, moving on. Now, it's just a generalization of semi-log function. So on the log linear plot, you've got log y equals mx plus c. Whereas on a linear log plot, it has y equals to m of log x plus c, where r is the base of the log scale. That's all. All right? So it's a different way of thinking about where your m will be, where your log will be, whether it's log y or log x. All right? So log y, you've got, when I sorted out just now, I rearranged the formula out just now, or the equation out just now, I know that is another log, that's another log number, that's all.
Or you log the x
Right.
instead of
Now go on to the log-log graph. Here, in this case, the x is a log, the y-axis is a log as well. And you can see that I've got function of x to the power of 2, x to the power of 3, and fx. When you plot it in the log-log graph, everything is a straight line.
Yeah.
Just notice one thing, log graph does not have a 0, all right? Because there's no log whatever equals to 0. There's no log 0, sorry, my fault. There's log 1 equals to 0. Now, so example 3 this time, can you show algebraically all exponential relationship of the form y equals to ax to the power n will appear as linear relationship on the log-log scale? Now, because you're looking at log scale, what you really need to do in this situation is take log on both sides. You need to take log of y and log of left hand side and log of right hand side. So if you take log of y, let's say log 10, base 10. Log of ax to the power of n is just log y equals to log a plus log x to the power of n, right? Because it's log ax, log of a times xn, which is log a plus log of x to the power of n. And you know that there will be n log x. Now log y is based on x. Log a is constant.
Yeah.
N is therefore the gradient, right? Yeah. So c equals mx again. Yeah. So can you therefore describe the gradient of the line formed by the line y equals x cubed on log in base 10? So if I do that, what would happen? A is actually 1, correct?
Probably just like.
So log y equals 3 log x. So therefore, I just indicated to you that it's a gradient. So for every increase in 1 unit of log x, there's an increase of 3 units of y. All right? Just a gradient, that's it. 1, 1, and 3. So a generalization, a log plot, you have a log y plus m of log x plus c, where r is the base of the log scale.
So can you go back one slide?
All right, actually, the 2 lessons goes on very smoothly. That really links to the application of log scale. All right. So that is your log plot and log plot and log linear plot. So what we're going to do is going to look at application of logarithmic scales.
PH.
Basically, this one, let's think about what we could do in terms of using the log scale. All right? I told you the log scale, things like Richter scale, things like pH scale, scale of loudness, musical scale, and there are a few other things that you can use. All right? So I'm going to give you 4 examples. Richter scale. Richter scale is comparing of the earthquake size.
Yes.
pH scale, measuring acidity or basicity. You know
Yes.
that you have come across that a lot. We don't really talk a lot about decibel, and unless you learn musical instrument, you wouldn't even really consider music scale. All right? So, you don't have to write all this down. If you need, all right, all this will be given in the exam. All right?
Yeah.
All this will be given in the exam. So what you need to think about the Richter scale is basically, it compared the size of the earthquake. It's developed in 1935 by Charles Richter. Magnitude of R, earthquake, is given by the intensity divided by the initial intensity, or the intensity of the smallest quake that can be felt by human. All right? So, therefore, by Richter scale, the smallest earthquake that can be felt by human is 0, because that divided by that is 1. All right? The smallest earthquake. So therefore, log of 1 equals to 0. And these are all based on log 10.
Yep.
It goes from 0 all the way up to 9. That's the Richter scale.
It keeps on going, so.
All right, now, example 1. How many times stronger is an earthquake of a magnitude 8 compared to an earthquake of a magnitude 5?
10 to the
So,
third,
if
3.
you look at that, how on earth are we going to use something like this? All right, here, it's just basically application of your law. So you can work out where earthquake of magnitude of 5 is log of I. Let's say that's earthquake I1 over I0. All right, that's the first earthquake, magnitude of 5. So therefore, I1 over I0 equals to 10 to the power of 5, because you're taking the log base 10. So therefore, the first earthquake will be 10 to the power of 5, I0, which is the smallest earthquake that we can feel. And then the second earthquake, Richter scale is 8, log is I2 over I0. So therefore, you can work out I2 and I1. So how many times you need to give me I2 divided by I1? Therefore, it is 1,000 times greater. So basically, using your idea of log scale, applying it, that's all. All right? So look at it as two separate events. Event number 1, the earthquake is a magnitude of 5. Event number 2, earthquake is a magnitude of 8. And work out what the I is, the intensity, based on I0. Work out intensity of I2 based on I0. You should be able to work out what that is, the magnitude. If this is log, take that will be 10 to the power of 5. All right? So the next one, early in the century, the earthquake in San Francisco registered 8.3 on the Richter scale. In the same year, another earthquake was recorded in South America. That was 4 times stronger. What was the magnitude of the earthquake in South America? So what I've done is I have just called that F and called that A. Just highlight so that I know what I'm doing. So what I do is work out the Richter scale. We know that the Richter scale for F is 8.3. So log of IF, intensity of San Francisco, over I0 is 8.3. All right? Now, we know that, therefore, IF is 10 to the power of 8. I0. Now, RA in South America, log A is IA equals I0. Since this is 4 times, so therefore it's 4 of this. 4 IF over I0. All right, because IA over I0, IA is 4 times stronger. So therefore is log of 4 times this. All right. And log 4 plus 8.3 log 10. So it's 8.9. Approximately 8.9. Use your calculator. It's approximately 8.9. So the idea is being able to use the formula, work out whatever it is, the Richter scale by I0. Here, I mean, it doesn't really have to be Richter scale, because later when I talk about the pH scale, we use the same idea as well. pH scale, you will use the same idea. All right?
Yeah.
Now, I'll move on. There's only 3 more examples. The pH scales. So you know that pH of 0 is very strong acidity, whereas pH of 14 is very strong base. All right? So 7 is neutral. The pH is actually potential of hydrogen scale. Measure the acidity or basicity of the solution. So it is calculated based on the formula pH is minus log of H plus, where H plus is the molar concentration of hydrogen ions in moles per liter. Right. So let's see how we could use this. pH equals to minus log H plus, the molar concentration of hydrogen. So pure water has a pH of 7. What is the hydrogen ion concentration of pure water? So let's think about that. pH of 7 7 is, you need to find out that, what H plus is. Alright? Just write that equation, substitute 7 in as your pH. So 7 equals, and minus 7 equals log H plus. So therefore H plus is 10 to the power of minus 7 moles per liter.
Did you do this in chem?
Yeah.
So
Well,
you
don't really do it this way.
you don't really do this stuff in chem.
Yeah.
You just know the pH, that's all. Alright? I learned this in maths, I don't learn this in chem.
Negative.
So I just know in chem you just look at the pH, you do the test and stuff like that. That's it. All right. So determine the pH for Coca-Cola, which has a hydrogen ion concentration of 0.03 moles per liter. So you know that the H plus is that. All right. So pH equals to minus of that. So therefore, is 0.003 is therefore 2.52 to 2 decimal places. It's just a practical
They don't give you
application.
that, but they just tell you.
All right, practical application of using the using your log.
It's a very acidic Coca-Cola.
Yeah, I don't drink Coke, so. Now,
Never licked in our streets up again.
scale of loudness. So it's really, you can think about how loud it is from really no noise at all, total silence, to breathing, to whisper, rustle of leaf, rain, refrigerator, so on and so forth. All right? I'm pretty sure when I teach, my pH will be, my pH, my decibel will be quite high. So here, the decibel scale is used to compare relatively sound intensity. The loudness of a sound L, measured by the decibel, dB is given by that. All right? Where there should be L, I don't know why I type I in. L, intensity of the sound in watts per square meters, and that is the I naught is the threshold of human hearing. The intensity of the sound just audible to the human hearing, which is known to be approximately 1 times 10 to the power minus 12. All right? I mean, in the actual application questions, all this will be given to you. You don't have to worry about the formula. You don't need to know that. All right? So what is the loudness of a sound that is at the threshold of a human hearing? You need to think about how you're going to work that out. How to work out I naught or L naught. I use I. So therefore, you use that divided by that, which is 1, which is 0 decibel. That's a 0. That's loudness of the sound. That is just threshold of human hearing. And then a sound double from 1 to 2. So 1 is 10 log of I1 over I2. All right, determine the increase in loudness. And log 2 is that 2I1 over I2. And you can work out 1 take away the other. This take away that. It's just 10 of 2I1. Log of 2I1 over I0. Take away log of I1 over I0. And that's it. Approximately 3 decibel. That divided by that is 2 log 2 is approximately 3 decibel. 10 times log 2 is about 3. Right, last but not the least, probably more applicable to a lot of music students. Anyone learn music? Yes. Yeah.
Barca.
You should know.
Barca's so good.
You should know the music skill. You should know what an octave is. An octave is between, like, for example, C to C, D to D, E to E, F to F, G to G. All right? So you think about that. 1 octave higher, the frequency is double the frequency. So if this is the middle C in the piano, this is one octave higher. The frequency of the C is actually double the frequency of that, the middle C. All right, if you learn the piano, you know what middle C is. That's where we normally start. The first lesson is always start with middle C. All right, so now, can you actually use a common law to rearrange to make X a subject? Pretty straightforward. you can just use log. Log 10 of f2 over f1 equal log of 2 to the power of x. And then that will be x of log 2. And therefore, rearranging, x equals to log of f1 take away f2 divided by log 2. Now, both of them will be useful. If you're given a situation like this, both of them will be useful. And I will show you one of the example I'll be using this, the other example I'll be using that. All right? This is especially important when you talk about 2 or 3 or 4 octaves higher. So this could be 1 octave. So another C above will be 2 octave, another C above will be 3 octave, another C above will be another octave. So the range around, if you think about soprano, soprano can probably sing up to around here.
Yes.
Another, yeah, that's approximately or a little bit higher. All right. So last example. The lowest note on the piano keyboard has a frequency of 27.5 and the highest note has a frequency of 4186 Hertz. How many octaves does the piano span? How many keys are there in the piano? 88 keys. 88 keys. All right. So what you do is use log of 4186 take away log of 227.5 divided by log 2. You have already derived that previously. So it's 7.25 octave. And then you can calculate the number of times the frequency is increased from a first note to a second note that is 4 octaves higher. So you will go quite high in that sense. This time I would use, because it is 4 octaves higher, I would use F2 divided by F1. I want that to be 4. I use division so that I know that will be 4. I can evaluate that. All right, because F2 is whatever. Sorry, 4 times log 2 is that. So you could work out log 2 to the power of 4 is that. F2 and F1. F2 over F1 is 2 to the power of 4. So F2 over F1 is 16, and therefore the frequency is increased by 16 times. So you can see that both of them, what you have derived, they are really useful. This one, you can actually think about one divided by the other and find the power to the power of 4, work out what the frequency is, the multiplication, the factor is, and therefore you know it's increased by 16. All right. I've actually finished 2 lessons in one.